Hi, and welcome to this look at an applied organic synthesis question which is based on aspirin. It includes a number of skills that quite often challenge people, such as dealing with an unseen mechanism or an apparently unseen mechanism, predicting the type of reaction in an unfamiliar reaction, and then working out a percentage yield. So let's do the unseen mechanism part. It gives you a reaction scheme, and it says in stage 2, which is here, it says it takes place by electrophilic substitution and part of the mechanism is shown to you. So the fact they've reminded you that it's electrophilic substitution should mean that it's possible to now start applying what you know about electrophilic substitution to this unseen electrophile. Now, the difficulty is that you've got carbon dioxide as the electrophile, which you won't have come across in a textbook before. Usually it's NO2 plus or Cl plus or Br plus or something like that. This is definitely outside the scope of A-level textbooks, but it can be done because once you realize that you're just dealing with the same type of mechanism as you've seen before, you can just transfer your ideas across. So thinking about what you probably remember from electrophilic substitution, you want to move an electron pair out of the delocalized pi system towards something that can behave as an electrophile. So that means an atom that's positive or delta positive is what you're after. Now carbon dioxide on its own is a neutral compound, so how do we deal with this? We have to think about the dipoles and the curly arrows first. So taking a closer look at the carbon dioxide molecule, you can apply your ideas about electronegativity. So oxygen is more electronegative than carbon, so O will get delta minus and C will get delta plus. And we can therefore put that in and start to put in the curly arrows. Now, I just want to explain where this curly arrow comes from. If you have a look down here, you've got a C single bond O and the O has a negative charge, so that the oxygen where I'm highlighting must have picked up 2 electrons. So the pi bond in the carbon dioxide C double bond O must have broken. Now it's just as possible you could put it in the top one. It doesn't matter which of the 2 bonds you put this curly arrow on. Now let's think about the structure of the intermediate that goes in the box. So taking what we worked out already, this time you have to think about what changes occur between the start of my mechanism and the end product. So if you have a look, now it should seem a bit more familiar. You've got your hydrogen to carbon bond breaking, you've got the curly arrow going back into the partially delocalized pi system, but notice the way I've orientated the U-shape. I've orientated it so the open part faces this carbon, because it's that carbon where the substitution is taking place. So I'm following it all the way around. In other words, I'm not taking this open part and lining it up over here or over here, over here somewhere. It's quite important to get that aspect right. So let's do a quick check of the mark scheme. So that's our first bit. It doesn't really matter, like I said, which way around you put it. You can put it to the top or the bottom. Now, what's interesting is all of these things have to be in place to get 1 mark. So you have to get this curly arrow, you have to get the dipoles in the carbon dioxide, and you have to get the second curly arrow. Now, when they say correct intermediate, there's a little bit of flexibility here. So my version and their version might initially look a little bit different, but essentially they're the same. Where they start to get a bit fussy is if you don't put in the U-shape in the right way. So this one here, for example, it doesn't follow all the way around. So it needs to only be open next to this carbon. It's not next to these carbons either. So this is actually not acceptable. So not many people make this kind of mistake, but it's important that they point it out, that the actual U-shape has to extend far enough around the ring so that it's only 1 carbon that isn't delocalized. Okay, so predicting the reaction type and the percentage yield calculation. So they want you to work out the type of reaction taking place during stage 1 and stage 3. So here's the reaction scheme again. So looking closely at it, you can see that you've got sodium hydroxide being used, and also the OH in phenol turns into O-. So therefore phenol is acting as an acid. But we've got to also take in stage 3. Now in stage 3 you've got a carboxylate ion attached directly to the benzene ring, and that becomes COOH again to change back into a carboxylic acid. So essentially overall you're getting neutralization. So in your explanation you've got to mention stage 1 and stage 3. So the carboxylate part of C6H5O minus COO minus gains a proton, and in stage 1 earlier on the phenol loses an H plus. So the next bit is the percentage yield. So taking a fresh sort of example of our reaction scheme, underneath it I'm just going to pop in a couple of things to consider. The moles of phenol is equal to the moles of salicylic acid, so they're equimolar. So if we know the amount of salicylic acid that we've made, we can use this mole ratio to predict the amount of phenol needed to do this, taking into account the 45% yield. Now we do know how much salicylic acid we've made, so we can calculate that. So that's 0.035 moles. So the expected number of moles of phenol needed would have been 0.035. But we need to scale up because it's only a 45% yield. It would have been 0.035 if it was 100% yield. So you're going to need more than that. So you do 100 over 45 to do that scaling up. So that gives you 0.0778 moles. So you multiply that by the molar mass of phenol, which is 94 grams per mole, to get the mass we require, which is 7.31 grams. So let's do a quick mark scheme check here as well. So they want neutralization, and they allow you to say it's an acid or base, or acid-base reaction, or both stage 1 and stage 3 involve proton transfer. There's a bit of flexibility there because this is quite a hard question. Now if you got 7.31, they award you 3 marks, and those are the 3 things you get the marks for. Now it's worth clarifying what else might be able to get marks on the percentage yield calculation. So I'm just going to have a quick look at that with you for a moment. So they always allow error carried forward at each stage, and it shows you what other things would also get some credit there. Okay, thanks for making it this far on the video. It's been quite a tricky question, isn't it? So as always, thanks for listening, and until next time, see you soon.